Thanks, Jackie, and thanks to the organizer for the invitation. I'm going to talk about some new results on spin hydrodynamics and chiral hydrodynamics. And I will talk about basically these 3 papers here, and many general things about spin and relativity are summarized in this review here, written with Nora Weigner. And yeah, so let's get to the point. So first of all, vorticity and spin physics in heavy ion collisions. So to start with this topic, I would like to first discuss a very famous phenomenon in condensed matter, which is the Barnett effect. So you take a ferromagnet, you rotate it, and then you will observe some magnetization along the rotation direction. And so the ferromagnet gets magnetized when it rotates. And the question we would like to address is whether some polarization through rotation can happen in heavy ion collision. And the answer actually is yes. So the reason is that in non-central heavy ion collisions, where the large or global orbital angular momentum can be transferred, at least in part, into the vorticity of the medium, the QGP, for example, and this will trigger in turn particle polarization in a way resembling the Barnett effect. So what happens here is basically the emergence of an effective interaction, the spin vorticity coupling, which couples, in fact, a quantum feature of the medium, the spin, and a classical feature of the spin of the particles, and the classical feature of the medium, which means the medium rotation. And this effective interaction, which emerges when fermions and all particles with spin are put into a rotating medium, triggers a lot of very interesting phenomena, like, for example, in the massless case, the chiral vortical effect, and in the massive case, actually, the lambda polarization. So the polarization of particles emitted from the fireball. And this was indeed observed by the STAR collaboration. This observation of the polarization of the lambdas variance along the direction of the global angular momentum was an extremely important experimental finding that deserved also the cover of Nature. And this showed that the quark-gluon plasma is the most vortical fluid ever observed. In fact, it was possible to estimate the vorticity through a thermal model, and it turned out to be many order of magnitudes higher than all possible rotating systems. For example, the great red spot of Jupiter is 25 order of magnitudes away. Again, the experimentalists also measure another polarization. So the polarization, so the same polarization of the lambda, but projected onto a different axis. So the polarization can be projected into any axis we want to. And it was measured the longitudinal polarization, namely the polarization of the lambda along the beam axis. And the important thing is that here, the same model that describes very well the global polarization actually failed in describing the local polarization. And these models were based on the assumption of local equilibrium of spin degrees of freedom. So this is called this mismatch in sign between these predictions and observables is called sign problem, and induced us to think whether spin actually plays a dynamical role in the evolution of the fireball. So that's the question that we would like to address, whether spin plays a dynamical role. So we know that relativistic hydrodynamics is a very powerful, effective theory in describing the evolution of the fireball. So now what we would like to develop is a theory of hydrodynamics which has the quantum features of the particles of the medium as a dynamical variable. So that's, of course, a conceptual problem because hydrodynamics is a classical theory and spin is a quantum variable. And so therefore the optimal starting point is to derive hydrodynamics from quantum field theory. And our starting point, starting point is to start with kinetic theory using the Wigner function formalism. Also, there are other approaches, which I will not discuss here. And so the object that we use to formulate kinetic theory is the Wigner function, as I said. But first of all, just an anticipation of the results is that what the message would be that this conversion, so this this alignment of spin along the rotation direction in a kinetic theory language is driven by non-local particle scatterings, where particles before scattering so that they have some finite orbital angular momentum that can be transferred into spin. And in hydrodynamics, this will translate into an antisymmetric part of the energy and momentum tensor. So quantum kinetic theory. So we start from the Wigner function, which is the Wigner transform of the correlation between two Dirac fields, correlated between two Dirac fields. The equations of motion from the Wigner function can be obtained by the Dirac equation. And we have that in the presence of a general interaction term that we call here rho, which can be derived of some interaction Lagrangian. We have a very general equations of motion. So now this formalism is very is suitable for studies of kinetic theory because these equations of motions imply a Boltzmann-like equation for the Wigner function and also an on-shell modification. So the Wigner function on shell will get modified, on shell relation will get modified through interactions. And therefore, we just want to write some Boltzmann equation for our Wigner function in the presence of this interaction, general interaction. So now just a discussion on how we do this, how we derive this, how we solve these equations of motion. We employ the H-bar expansion, which is effectively a gradient expansion. So this is because of the form of the equations of motion of the Wigner function. But the procedure is that we expand in H-bar, in powers on H-bar, so we expand around the classical value of the Wigner function. Furthermore, we also need to expand the collision term in terms of H-bar and in terms of the non-locality of particle scattering. And this non-locality, which will be a gradient expansion, will emerge very nicely in this formalism that is also an H-bar expansion. Also, we have a third kind of expansion, which is the expansion around equilibrium. And this is also, we assume, this is our assumption that these deviations from equilibrium are, again, gradients on order of H-bar. So this is a little bit of technical slide here in which I discuss how we include spin in the phase space. So we enlarge spin in we enlarge the phase space to include classical variable which takes into account the spin dynamics. And this leads us to define a new Wigner function, which I call f here, this Gothic f, which is expressed in terms of some components of the Wigner function. So the Wigner function can be decomposed into the Clifford algebra, but not all components are independent. And we will focus into a component which is related to the scalar part, this f here, and the axial vector component. And so this will be sufficient to describe the whole evolution of the Wigner function. And once we have these components of the Wigner function, scalar and axial vector, we can calculate our microscopic quantities for the development of hydrodynamics. So then the moral here is that you can cast the complicated evolution of the Wigner function into one scalar equation. And here I will not go too much into the details, but again, I just want to show the final results. So again, we have the local and the non-local term, so in our expansion. And after very lengthy calculation, one can prove that the final result is indeed intuitive. So we have that the collision term looks very similar to the usual Boltzmann collision term. However, now we have these deltas here, which are space-time displacements, which take into account of this non-locality. So the scatterings will not happen in one single point, but there will be some impact parameter. Also, another feature of this quantum treatment is that we also have a contribution. We have two contributions for the collision term. One, which takes into account only momentum and spin exchange. So, and another one, this one in sort of brown, considers only spin exchange terms. And the transition amplitudes here, this W's here, contains also the dependence on the spinning phase space. So this is just to show the structure, which I think is a very intuitive one. So now we want to study the equilibrium condition for this collision term, and to do so, we search for the conditions such that the collision term vanish. So we use an ansatz for the distribution function. So we actually working in the low density approximation. I should have said that before. So we have a Boltzmann-like equation, a Boltzmann-like form of the distribution function, in which now the point is that we should not only consider as a conserved charge the energy and momentum, but also the total angular momentum. And this coupling here, which resembles the spin-vorticity coupling, takes into account this total angular momentum conservation. And this omega mu nu are called the spin potential and are the Lagrange multiplier associated to the angular momentum conservation. And this dipole moment tensor is the tensor which describes spin in phase space. So by inserting this equilibrium form into the collision kernel that I showed before, it is possible to show, I will not show it here, but I have some backup slide in case you are interested, that the condition for the collision term to vanish is the global equilibrium condition. So we didn't find any standard local equilibrium condition for this. So this, once we have our kinetic theory, we can go to spin hydrodynamics. And what do we mean by spin hydrodynamics? We mean that we include into the evolution equations, the usual evolution equation of hydrodynamics, the conservation of the total angular momentum. So if we start from some quantum field theory, we can define the orbital and spin-like part of the total angular momentum. And we include as a new dynamical variable the spin tensor, the so-called spin tensor, which takes into account the spin dynamics. So for scalar fields, the spin tensor is 0. And so now we want to we calculate from our quantum field theory our microscopic quantities. And then we have these new evolutions, as I said. And the new unknowns, so will be besides the usual for velocity, beta mu, velocity over temperature, we also have the spin potential. So now there is a point to make, and we'll not go into details here, but if you're interested in our review, we went quite a lot in details. That there are the densities are not uniquely defined, so you can reshuffle density between energy momentum tensor and spin tensor such that the total charges are the same. And this leads to ambiguity in the definition, and there are many choices in the literature. For example, the canonical choice, which is used for example, applying the Nether's theorem to our Lagrangian, turns out to have a bad definition of spin in the sense that the total spin is actually not a tensor for free fields. So this, we consider this not a desirable feature, and we use the solution proposed many decades ago by these two Dutch guys, Hilgevoord-Wouthuysen. And therefore, we construct our spin hydrodynamics equations of motion using these currents. So now what comes here is that the energy momentum conservation in this pseudo gauge, so this HW means the pseudo gauge, has a very simple interpretation. So the P here, we have the collisional invariant. So the momentum is a collisional invariant. However, when it comes to consider the non-conservation of the spin tensor, we relate it in this pseudo gauge to the integral in phase space of this spin dipole moment tensor and the collision term, which defines the antisymmetric part of the energy momentum tensor. Some discussion here. So in the case of non-local collision, in general, spin is not conserved. So the spin dipole moment tensor is also not conserved. This means that in general, an antisymmetric part of the energy momentum tensor will arise because this integral will be different from zero. And therefore, we can describe the conversion between orbital and spin angular momentum. However, in local equilibrium, spin is a collisional invariant. Therefore, no antisymmetric part of the energy momentum tensor because this integral is zero, so the spin tensor is conserved. And also in global equilibrium, the spin tensor is conserved because the collision term is identically zero. Therefore, we conclude that in local collisions, at least away from global equilibrium, the dynamics is always dissipative. And this also agrees with some non-relativistic cases discussed in the literature, also fluid dynamics for non-relativistic systems with the internal degrees of freedom. And therefore, we have a framework which produces some polarized medium through non-local collisions. However, the question is still what is the meaning of the local equilibrium in this kind of theories when non-local collisions are included. So we will see also this in another perspective. Namely, we also started to look at chiral hydrodynamics under a different point of view. And chiral physics is also sort of spin physics. So we have this effective interaction which still triggers the chiral vortical effect. And this is the usual chiral hydrodynamics, viscous hydrodynamics, introduced by Son and Surovka. These are sort of standard now. It's a pioneer work here in which they introduced these new constitutive relations, in which we have, besides the usual Navier-Stokes, we have the term which is responsible for the chiral vortical effect. So the term proportional to the vorticity omega and the new transport coefficient. The new term with the chiral magnetic effect, and with the new transport coefficient. So the current will also acquire contribution along the magnetic field. This B is the magnetic field. So the equations of motion read in this form here. So the current here is, if it's an axial current, is not conserved because we have the anomaly, and this C is the anomaly coefficient. So this is a great result. However, the question one should ask is, can we indeed solve this? So can we find, once we give the initial conditions, a solution? So this is the initial value problem in standard theory of partial differential equations, the Cauchy problem. So we have in general a nonlinear system of partial differential equations. And it can be cast in this form, also our hydro with respect to this form. The highest order derivative will have a coefficient which is called the principal part. So the initial value problem means that once we have some initial condition, which in physics are normally taken in time zero, initial time of our unknowns, psi of our unknowns, we need to find a solution. So the minimal requirement for the solution to be found is that we should express the highest order derivative with the initial data, because this is how we can eventually construct a power series for the solution, so we can find a solution. This is sort of a minimal requirement. This means that the coefficient of the matrix of the coefficients of the highest order derivative has to be invertible, because we need to express in terms of the other terms. So this means that the so-called characteristic determinant has to be different from 0. So as a consequence, we also need to discuss the well-posed theory. So we say that the initial value problem is locally well-posed in some function space, for example, analytic functions, along some hypersurface. If for arbitrary initial data, it's very important that the initial data have to be arbitrary. There exists some unique solution in the neighborhood of the hypersurface. Also, that small changes in the initial data will influence small changes in the solution. So this continuity between small initial data and solution. And also for relativistic theories, it's crucial that causality holds. So examples that of well-posed theories are ideal hydrodynamics. So Klein-Gordon, for example, theory, general relativity. So we can select already if a system is ill-posed by calculating the determinant of the principal value, so the characteristic determinant. If this determinant is 0, then we can already say that the system itself is ill-posed, and we cannot find a unique solution for arbitrary data. So now we study again the Chiral viscous hydro derived by Son and Surovka, and we see that if we calculate the characteristic determinant here, it's very easy to see that one column is 0, and therefore the determinant is identically 0. So this theory is actually ill-posed and also acausal. And we note in passing that the Landau-Lifshitz that can be obtained by setting all these anomalous terms and the electromagnetic field to 0 has the same characteristic determinant as this Chiral hydro. And therefore, this Landau-Lifshitz is also ill-posed and acausal, and also it's unstable, actually. So the question is how this issue is due to viscosity, because we know that Landau-Lifshitz has problems because when we introduce viscous terms. So we can study this with the ideal Chiral hydrodynamics derived from kinetic theory by some authors, including its reference here. And we have that in general, the energy momentum tensor has some contribution to the heat flow due to vorticity, sort of heat flow. So we see that this system of equations here, which is standard, also can be proven to have a characteristic determinant equals 0 for any identically equals 0. So this means that this system is also ill-posed in the ideal case. And this is very different from the usual ideal hydrodynamics where it's well-posed. So this is, of course, brings some conceptual issues when it comes to include chirality into hydrodynamics, because we cannot really evolve this system. And how can we fix this? So here, of course, we don't have an answer. We have just suggestions. For example, this new newly developed theory by Benfica, Visconsi, Noronha, and Kovtun may fix the problem, because the introduction of new term in this theory can will change the characteristic determinant, so it should fix the problem. Also, we know because without chirality and spin, the theory turns out to be well-posed and causal and stable. Also, we need to study this. We don't know in the presence of chirality how this works, but we are positive that it's going to solve the problem. But still the question is posed whether is also Chiral hydrodynamics always dissipative, in the sense that if we want to solve it, should be always dissipative. So as I showed in the first part of the talk, spin hydrodynamics turns out to be, from quantum kinetic theory, turns out to be always dissipative. And so again, the question, what does local equilibrium mean in such theories? Whether if the theory is always, if the system is always dissipative. So with this, basically, I conclude, and I believe that this is a sort of new era where spin degrees of freedom have to be taken into the hydrodynamics and kinetic theory description of the quantum fluids. also because there are new experimental observables, also that quantum field theory, as I said, would suggest that the dynamics in presence of spin would be always, and in presence of nonlocal particle scatterings are always dissipative, and that standard chiral viscous hydrodynamics or chiral hydrodynamic from kinetic theory, which is dissipationless, are unfortunately ill-posed and acausal. And yeah, so this I think will bring some conceptual issues that have to be clarified with further studies. Thank you.
Thank you, Enrico, for this nice talk. You already have some questions that have been forming during it. So let's go, I think, to slide 18, and Uli has a question.
Yeah, so the first equation says that the total energy momentum tensor is conserved. The second equation says that the antisymmetric part of this is given by the spin divergence of the spin tensor. Is that part separately conserved, or is in the conservation law for energy a possibility to transfer from symmetric to antisymmetric components?
No, these two are independent. So when you have spin, so
this just says what the antisymmetric part of T mu nu is.
Yes, but we also know.
But it doesn't tell me what the divergence of that antisymmetric part is.
Of this antisymmetric, of which divergence?
Yes.
Of the divergence of this? No.
Yes.
No, this is valid for both the symmetric and the antisymmetric part of the energy momentum tensor here.
Separately.
This
okay,
is
yeah.
this
That's
this
what I
is
thought, yeah.
yeah. This is simply, one can see it also from quantum field theory, for example, the Noether's theorem, that you have if you say that your theory, your Lagrangian, is invariant under space-time translation, then you get that partial mu T mu nu is equal 0. Then if you also say that it's invariant under Lorentz transformations, then you get this here. So which which is this equation here. So this doesn't need any kinetic theory input to be formulated in principle. But we just sort of match this conservation law with kinetic theory.
So the conservation of the antisymmetric part of T mu nu, what symmetry does that reflect?
It doesn't. It's not related to any symmetry, I think.
Okay.
All right. I know Travis has a question. Do you want to unmute yourself, Travis?
Sure. Yeah. Just maybe a simple question, but is it obvious that observables in the hydrodynamic limit don't depend on your choice of pseudo gauge, or is it going to be shown?
No, here I actually didn't show. I didn't show this. Unfortunately, I don't even have Becker's slides on this. But one can show that in general, observables actually depends on the expectation value of operators depend on the choice of the pseudo gauge. Actually, in general, if the system is away from global equilibrium, at least, we can reduce this statement in this. Unfortunately, I don't have a supplementary slide for this, but this means that if you calculate an observable, which doesn't have to be in general conserved charge, but just an observable, this will be will in general depend on the pseudo gauge. Because if you write the expectation value here, you can write it in quantum field theory as a sort of trace with some statistical operator, and you can show that the statistical operator is actually a pseudo gauge dependent quantity if the system is away from global equilibrium. Yeah,
it's really interesting. That's just as a comment on that. That's very reminiscent of the problem that appears that BDNK solves. It's kind of like it reminds me of a hydrodynamic frame in spirit, where it's like you have, I don't know, and it's funny that it leads to acausalities. But okay, great, thank you.
Sure.
All right. So next up we have Shrondroy.
Yeah, hi, Enrico.
Hi.
So the thing is, when you have non-local collisions, then T mu nu has an antisymmetric part, right?
T mu nu, yes.
But that appears only at order h bar square.
Right. Yes.
In your power counting scheme at order
Yeah,
gradient.
yes, that's right. Yes, here.
Right.
So this is so it has to next to leading order. Yes.
But then
Here.
kinematic vorticity goes as first order in gradient or in your counting scheme order
Yeah.
H bar. So how do you relate these two, the spin and vorticity, in the power counting scheme?
So that's basically, I can answer this question in this way. So here, if you see here, so we are trying now just to mathematically solve this these equations of motion here. So if you see here on the left-hand side, for example, which is more cleaner, when you have an H bar, you also have a gradient.
Mm-hmm.
So this means that if you are expanding in H bar, you're not just expanding in H bar, also for bidimensional analysis actually. But you have to have some gradient, and in principle also some mass on the denominator, some mass scale. And so this is just to say that H bar and gradients are all the same. So the non-locality is a gradient expansion, and it emerges, it arises very naturally, that if you write down this in a more probably less compact way, you see that these non-local terms have this structure here as H bar partial. So this means that the terms that are normally dropped, the usual kinetic theory, actually have order H bar in this non-locality. If you just consider systematic H bar expansion in this way. So this is basically, again, the H bar gradients are all together. They are together.
Okay.
Yeah,
Thanks.
sure.
Okay, so there's a question from Misha.
Hi, can you hear me?
Hi, yes, hi.
Hi, Enrico. Very nice talk. Thank you. I might have missed. Could you go to the slides where you discussed the problems with Chiral hydrodynamics, in particular that characteristic determinant is 0? I am not sure I caught the point of what actually makes what ingredient of this makes it problematic. So, for example, if I set the coefficient C to 0,
the coefficient C, sorry, the xi, you mean this?
Yeah, all xi to 0. So if I go back to ordinary hydrodynamics, are you saying that
it's also bad, because actually the characteristic, because the characteristic determinant is the same. The reason is, so when you calculate the characteristic determinant, you calculate, so you take the equations of motion here, right? And therefore, it means that you need to take the partial derivative of J and T, right? So when you take the partial derivative of omega, due to the fact that omega has an epsilon, so you will always have partial U term, right? So this means that it will not contribute to the highest order derivative. It will not contribute to the principal part, but it will only contribute on a term like this. Do you see my cursor?
Yes.
So this means that the inclusion of the omega actually doesn't modify the principal part of the Landau-Lifshitz. So because
that's what, yeah, that's my starting point. But if it doesn't, then, and if ideal hydrodynamics has no problem, as you are saying,
no problem,
right?
no, because we only.
So how if inclusion of omega doesn't modify the principal part, how does this problem appear when I include omega?
The thing is that if you go, yeah, that's exactly the question we would like to address. So if we start, so we agree, right, that usual ideal hydrodynamics doesn't have any problem, right? Usual ideal.
I thought so. Yes.
Yeah, it has.
Yes.
I can guarantee this. Yes.
Yes.
So, but Landau-Lifshitz has. So now, if we go to the
first order hydro, that's a different question, which I would like to. But suppose forget about Landau-Lifshitz. Let's just consider non-dissipative chiral hydrodynamics without viscosity.
Yeah.
Just,
for example,
just these terms.
These terms.
Yes.
Yes.
So you are saying that characteristic determinant in this case is 0.
Right. Yes. Unfortunately,
Right?
yes. Yeah.
But if you drop the blue terms, then it is not 0. Is
Right.
that correct?
Correct.
So how can this happen?
Because of the principal part is modified now, because we have the derivative also brought by the omega, by the vorticity. So here it's a different story. If we have ideal hydro, we will only have derivatives applied to the velocity or to the energy, the thermodynamic quantities. But here we will also have a partial that will act on the vorticity, and we will have a second order here because we will also have that when you act the partial onto this heat flow, let's say, term, when you contract, for example, u mu, partial mu applied on omega nu, you will have the second order term, because this will have a second derivative, because you will have total derivative.
Maybe I'm so I suspect that the problem is the same as in Eckert, because you have so original Surovka, Son Surovka work in Landau frame.
Right.
So psi t is 0.
Yes.
So in that situation, I do not see how you can generate zero determinant if you just turn on the anomaly. That's what I fail to see.
That situation is trickier, and I'll tell you why. Because that situation, we don't have a simple, we don't have this form of the equation. So you are saying,
yes.
If you're saying, if I just
if you just do
psi 0, right? Set I and sigma 0. So the problem is that we will not have as he called quasi-linear PDE, because this term will not be there, but we will have actually a non-linear term already in the highest order derivative, because we will have A that is equal 0 and B which is different from 0. In this case, is not so straightforward. So, and that's we don't know yet this.
You don't know yet. Okay. Yes.
But yes, because the form of the PDE is totally different, because now we have a partial differential equations in which the highest order is non-linear. So you see here is different, and that's another story. But somehow the theory by this sort of BDNK theory, as now it's called, show that this Landau frame is not really a good choice anyways, because of all this causality and well-posedness and causality. So now we just want to see actually what happens with chirality also, and to study well-posedness in this context. But yes, it's true. What you're saying is true. But again, this ideal from kinetic theory that you also derived in your paper, this here somehow, if you put this heat flow, that seems that doesn't work either.
I think,
we are puzzled.
Yes, I think I see what you mean. Yeah, so it is that. But isn't it the same reason why Eckert frame is worse than Landau? That it has a similar problem.
I don't think so.
No, Eckert is different. Eckert is not ill-posed. Eckert is a causal right away, as you know, but it doesn't have.
But it is not in pole.
Yeah, it doesn't have that right away. Yeah.
But we do have this similar term. Instead of omega, we have heat flux there. But Enrico is telling me that it's the presence of u nu, which appear, and this heat flux actually contains a time derivative.
Yeah,
right?
so I think we should talk about this in the discussion.
Okay.
It's a little bit different, but it's a very good point. We should go back to this.
Okay, I understand. Thank you.
Sure.
Yeah, along that line, I think there's a huge amount of discussion in the chat that looks quite interesting. I think we should move that then to the discussion in the afternoon, because it looks like there's a lot to unpack here. But thank you very much, Enrico, for this nice talk. That seems to be huge amounts of discussion. So
thank you.
Speakers once again. And then I know that there's a break, so I don't know.